let's look at the process of vaporization. So if we have a liquid like water, that liquid can vaporize, go to the gas phase, and this particular process is called vaporization. And there is an energy associated with this process of vaporization for any liquid. You should recognize it's going to be an endothermic process. You're going to need to put energy into liquid water or any other liquid to separate the molecules in the liquid so that they can become gaseous in the gas phase. We symbolize the enthalpy associated with this process, delta H subscript vape, which stands for the enthalpy of vaporization. You should recognize that the opposite of this process is the process of a gas going to a liquid. This is known as condensation. We could write the energy change associated with this as delta H cond for the enthalpy of condensation, and we should recognize that this is going to be the opposite of whatever the enthalpy of vaporization is. Now for water, it turns out that the enthalpy of vaporization for water is 40.7 kilojoules per mole. Given this information, let's figure out how much energy is released when enough water vapor in the air condenses to rain to cover a depth of 1 centimeter over a square kilometer. So to attack this problem, we're first going to need to know how much water is going to be in this volume. So we're going to imagine a square kilometer, 1 kilometer on each side, and then the depth of that kilometer is going to be 1 centimeter. Of course, this is not to scale. We want the volume of this so that we can then convert it into a mass. Once we get that mass in grams, we'll be able to convert that to moles because we know that for water, 1 mole of water is 18 grams of water. Then we can find out how much energy is released. So let's figure this out. The volume is going to be the length times the width times the height, but these units don't talk to each other, right? We got kilometers and we got centimeters. Because I know the density of water in grams per centimeter cubed, it's 1 gram per centimeter cubed, I want to convert all of these to kilometers, to centimeters, So I'm going to get out my handy chart here. If you remember, kilo, hecto, deca, our base unit, deci, centi. If I have 1 kilometer, that's going to be 100,000 centimeters. So the volume of water in this particular case is going to be 100,000 centimeters. That's the length times the width, which is another 100,000 centimeters. So let's just square this. So that's this times the height at 1 centimeter. All right, doing the arithmetic. 100,000 times 100,000 times 1. It's going to be 1 times 10 to the 10th centimeters cubed. And since the density of water is 1 gram per centimeter cubed, that's going to be a mass of 1 times 10 to the 10th grams of water. So we have the mass of water that we need to fill this volume. All right, now once again, we're going to remember that the enthalpy of vaporization of water is 40.7 kilojoules per mole. And we know that we have 1 times 10 to the 10th grams of water. Now, vaporization is liquid water going to gaseous water. And we've got to remember that in our problem, we're condensing gaseous water out of the air into liquid droplets. So while the enthalpy of vaporization is what we're given, that's a positive 40.7 kilojoules per mole. Our enthalpy of condensation is going to be the opposite of this. So this will be the energy released. And we have the number of grams of water that were required to fill our volume. That was 1 kilometer squared and 1 centimeter in height. So we know that this is the amount of water in grams to fill this. We're going to need to convert it into moles so that it'll talk to this particular quantity that we have here. And that's an easy enough calculation, right? 1 times 10 to the 10th grams of water. We know that there are 18 grams of water for every mole of water. And then using this here, we know that for every mole of water, there's going to be 40.7 kilojoules of energy released. Running through the arithmetic, we will have 1 times 10 to the 10th. We're going to divide that by 18, and we're going to multiply that by 40.7. Well, that's a lot of energy. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be 22.6 times 10 to the 9th kilojoules of energy that's going to need to be released. And to give you some context of this, it is known that some nuclear bombs release of energy of about 100 terajoules. At least some of the first atomic bombs released about this much energy. So, you know, for how much energy is released into the atmosphere to condense enough water vapor to cover this amount of volume, we can sort of get an idea of how many nuclear bombs worth of energy that must release. So to do this, we need these units talking to each other. So let's see, it goes tera, giga, mega, kilo. And I've got what, 100 terajoules of energy. 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like 100 times 10 to the 9th kilojoules is the same as 100 terajoules of energy. And so it looks like this is roughly a fifth to a quarter of the amount of energy as that released by one of the earliest nuclear bombs. It's pretty remarkable. For the next problem we're going to do, we're going to calculate how much energy is required to boil 4 cups of water at 100 Celsius. So how much energy is required to boil 4 cups of water at 100 degrees Celsius. And we're going to use the conversion factor that 1 cup is 237 milliliters. And because water is 1 gram per milliliter, that'll be 237 grams. It's the same kind of question. We can still use the enthalpy of vaporization of water, 40.7 kilojoules per mole. We still have that quantity as well. I'll write that over here. Delta H of vape, 40.7 kilojoules per mole. Well, I'll start with the quantity I'm given. 4 cups of water. I'll use this conversion factor here. 1 cup of water is 237 grams of water. We're given the quantity grams, but our energy amount is given in kilojoules per mole, so I'm going to need to convert these to mole. And once again, 18 grams of water is 1 mole of water. And now that I've converted this quantity in cups to moles of water, I can use this factor here. 40.7 kilojoules are going to be released, need to be required, need to be put into the water for every mole of water that's vaporized. Doing the math, 4 times 237, we're going to divide that by 18, and we're going to multiply that by 40.7. It looks like it's going to be about 2,100, roughly speaking, kilojoules of energy are going to need to be pumped into the water to get it to boil.